This example demonstrates very well the core problems of using p-value driven hypothesis testing. Suppose that we add this double-headed coin to a bag containing 999 fair coins, and let's suppose that we select a coin at random and toss it 100 times to test the hypothesis H that the coin is fair, i.e. not double-headed. And as good experimenters, we set the p-value 0.05 in advance. Suppose we get 55 heads out of 100, then the probability of getting that evidence, if the hypothesis is true, fair coin, is 4.85%. That's less than 5%, so we can reject the null hypothesis at the 5% level. Are we 95% certain that the coin is not fair? No, in fact it's 100% certain that the coin is fair. In fact, for a fair coin, there's a probability of 18.4% of getting at least 55 heads in 100 tosses. So there's an 18.4% chance that the p-value test will wrongly conclude that the coin is double-headed. Let's see how I got those calculations by using a simple Bayesian network model in AgenaRisk. Here's the model. Let's see how it's defined. First of all, how is the fair coin defined? Well, the prior probability there is 1 over 1,000 that it's false and 999 over 1,000 that it's true. Probability of heads is defined as 1 if it's false and 0.5 if it's true. The number of heads in n tosses is defined as a binomial distribution, where the number of trials is simply the number of tosses, and the probability of success is simply the probability of heads. So there's the probability distribution. Now if we set the fair coin to be true, that observation to be true, and run the model, these distributions change a little bit because that was already a very strong prior, and let's look at what the probability of getting particular numbers of heads are. The probability of getting 55 you can see is 0.04874. In fact, we can actually display all of these. And there you see the probability of getting exactly 55 is 0.48474. And the probability of getting a number greater than 54 is 18.41%. Now let's copy that node and paste it, and we can see the probability of getting greater than 60 heads. So we're just going to define this exactly the same, but we're just going to change the definition here. So we change that to 60 instead of 54. And we run the model again. And there you can see there's a 1.76% probability that you get greater than 60 heads.